It's all about friction. Um, can anybody tell me what friction is? Or tell me anything about friction?
Like when you like when you're running on a carpet with
Hmm.
like socks on and it like starts to burn.
Yeah, yeah, that is an example of friction. So one thing about friction, you guys, and we're going to talk about this, is that a byproduct of friction is heat, always. So there's always a byproduct of, or there, heat's always produced when there's friction. Um, and how do you produce friction? Well, we already have kind of an example. You're when we're walking on a carpet, right? In our socks, we can feel that heat on our socks. What are we kind of doing there when we're walking on the surface and we're creating friction?
They're like rubbing together.
Yeah, that's exactly right. So anytime two surfaces rub together, it produces friction. So let's go to our next slide here. All right. And there's a lot of stuff on this slide, but let's talk about the first thing. All right. Actually, you know what? Let's kind of do it one by one. So the two surfaces have to be rubbing together to have friction, or be sliding past each other. Same type of thing. Okay. So I have to have two surfaces. If I only have one surface, I can't have friction. So actually, if I have a spaceship in outer space, and outer space isn't a perfect vacuum. And remember, in physics, when we say vacuum, what we really mean there is that there's no air, there's no other particles, but it's pretty close. So in space, if I have a rocket ship flying through outer space, there's no friction. The reason there's no friction is because there's not a second surface. It's only one thing, right? In order to have friction, you have to have two surfaces. So when the space shuttle or the rocket, whatever we have that's launching, the only time it experiences friction, you guys, is when it's going through our atmosphere. Lots of friction there. And then when it gets out of the atmosphere and it gets into deep space, no friction. All right. Now, the other thing to know about friction is that it's caused by the roughness of the surfaces. So if the surfaces were perfectly smooth, think of the best ice that's almost perfectly smooth. Zamboni just went across it. Um, you know, in those cases, there's very little friction, right? Um, the rougher the surface, the more friction. The smoother the surface, the less friction. And a lot of times, you guys, sometimes the roughness can be on a small scale, but sometimes you can see it. Like, think about sandpaper. If you take sandpaper and you try to push it across a piece of wood, you can feel the friction. And if you rub wood on sandpaper like really hard, you do it repeatedly, you can feel that heat. So once again, that's not on this slide, but heat is always a byproduct of friction. And I want you guys to think about when you're cold. When you're cold, your hands get cold. One of the things that you do is you hold them together and you rub them, right? Like, everybody take a second right now in your house. I can't see you, most of you, but I'm going to assume that you're going to do it with me. So just take your hands, put them together, and rub them hard. And if you do that, you can feel that they heat up, right? So also, if you do that, if you do it really hard, and then you look at your hands, you'll see like dead skin and stuff. That doesn't mean that you're a dirty person, right? That's just normal. Um, you're always sloughing off skin cells, and that the friction is actually, and the roughness of your hands is actually like just pulling that stuff off of the top layer. Okay. Um, Now, friction is also always an opposing force. So friction always opposes motion. Now, that doesn't mean that friction is always bad. Sometimes we want to reduce friction, but sometimes we don't. And I'll give you an example. Um, in about a month, we're going to be back at Leiden, a lot of us, right? And if you're walking from, say, your math class to your physics class, when you walk in the hallway, you want there to be friction. Would you rather walk on a tile floor in good shoes, or would you rather try to walk on floors that I iced up? Um, that you wouldn't want to do that, right? Um, so when you're walking and you're getting from place to place, you rely on the fact that there's friction between your feet and the ground to propel you forward. If there was no friction, you actually wouldn't move anywhere. You would just stay in one spot. It would be like a Scooby Doo cartoon, if you've ever seen that, where they run, 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 and they don't actually go anywhere for a while, right? So friction's not always a bad thing, but it is always an opposing force. It always opposes motion. Now, the other one thing that I skipped over here a little bit is not only is friction caused by the roughness of the surfaces, it's actually how hard the surfaces are pushed together. So if we go back to our hand example, if you take your hands and even if you move them really fast, if you're barely touching them, if you're not pushing them together hard, they don't get that hot. But if you push your hands together hard, you don't even have to be moving them that fast, they get pretty hot, right? So the force that pushes the surfaces together, that increases the friction if it's bigger, and it decreases the friction if it's smaller. Now, a lot of times, you guys, this is what leads to a lot of confusion in your heads about what forces make objects actually stop moving. I'm going to tell you that gravity, if I have a box on the floor and I slide it, gravity is not making that box stop. It's not. Okay, gravity is pushing it down towards the center of the earth. And if I slide it on the floor, the box is trying to move forward. The force of gravity and the direction of travel, they're not in the same direction at all, right? But gravity does, the amount of gravity or the weight of the object on the floor, that does increase the amount of friction. And it increases the amount of friction because it's increasing how hard the surfaces are getting pushed together. Okay? But gravity by itself isn't what stops something. And once again, we'll use the example of a hockey puck on ice. If I put a hockey puck on ice and the ice is really, really slick ice, it's really smooth, I could just give that hockey puck a little tap and it'll move all the way across the rink. Okay? That happens because there's no friction. It didn't happen because I turned gravity off. Does that make sense to everybody? What was that?
Okay. So there's no scenario where gravity by itself is stopping any motion.
Well, so there's no scenario where you're sliding something, say across a flat surface, like a floor, where gravity is stopping it. The only scenario where gravity would be stopping an object is if you threw it up. Like when we took our projectiles, we threw them straight up. Now the direction of travel is in the same direction as the gravitational force.
Oh, that makes sense.
Yeah. Okay, so this is the basics on friction. I know there's, like I said, I know there's a lot on that slide, you guys, but it's all kind of important stuff. Now, we have a special name for the force that pushes two objects together. And the force that pushes two objects together is called the normal force. Now, normal, that's a geometry term. I don't mean normal as in, you're the average person. You're not like a weirdo or something, right? That's not what I mean. Normal means perpendicular. So the force that's perpendicular to the surface is called the normal force. And that force is the force that's pushing the two objects together. Now your book uses this notation. It uses a capital N. I'm actually going to draw it a little differently when I draw this out. And when I write it, my pen's acting a little crazy. Give me a second. Okay. When I write it out, I'm going to write it like this. An F with this little symbol. Okay? So you'll see it both ways. Let me rewrite that because that did not come out well. So it's an F with this little symbol. This little symbol, you've seen this in math class. I know you have seen it. It means perpendicular. Okay? So this would be the perpendicular force or the normal force.
So how will we know if it's I'm guessing based off what the question's asking, we should know which one, if they're using newtons or normal.
Okay, so newtons is just a unit. This is a good question. Newtons is the unit. Every time that we do this problem, and this is why I don't like to use this capital N, right? Because it's easy to confuse this capital N as a variable with our unit of newtons. So we aren't actually going to use this in our equation. I have it. I'm going to show you on the next slide, but we're going to write it differently. Instead of writing this N, instead of writing this N like this, we're going to write it like this. Okay, so this will be the symbol for the normal force. This is going to be the normal force. That is how we're going to write it. Okay, you guys, you're going to have to give me a second. There is a problem. Sometimes I need to reset the setting. Otherwise, this is going to be a long day. Okay, everything looks good. Sometimes I just have to launch that and then this starts working. Sorry about that. Let me rewrite this. So the normal force symbol is going to be this one. So this we'll always use this to represent the normal force. Okay, I just wanted to show you this because that's what your book uses. Some books use this, some books use this. They mean the same thing. Now, if I'm on a flat surface, okay, like a table, let's say I'm sliding a box on a table, the normal force is going to be equal to the weight, right? The weight of the object is what pushes it into the surface. So the weight of the object is what's squeezing it into the surface. And remember that weight is mass times gravity. So this is equal to the weight. That was my public service announcement yesterday, right? Weight and mass aren't the same. Weight is mass times gravity. So you guys, so we know that normal force, that perpendicular force squeezing the two objects together, that is going to be important. We're going to use that to calculate the amount of friction. The other thing we're going to use to calculate the amount of friction is the roughness of the two surfaces. Now, we have a quantity, and it's called the coefficient of friction. So the coefficient of friction measures the roughness of the two surfaces. And what the coefficient of friction tells you, it tells you what percentage of the normal force gets translated into friction. Now, it's actually possible to be more than 100%. So in most of our physics problems, the coefficient of friction will be between 0 and 1. If the coefficient of friction is 0, that means there's absolutely zero friction. None of the normal force ends up being translated into friction. If the coefficient of friction is 1, that means 100% of that normal force will be translated into friction. So if the weight of an object was 100 and the coefficient of friction was 1, friction would be 100. If the weight of the object was 100 and the coefficient of friction was 0.5, right, only 50% of it gets translated, so the friction would be 50. But it is actually possible for the coefficient of friction to be more than 1. It can be possible that the surfaces have such a hard time sliding past each other that friction is actually bigger than the weight of the object, or the force that's pushing them together. Now, can I show you the equation and exactly how it works? Or do you need to write stuff down still?
I'm finished writing.
Okay.
Wait, so if the coefficient is 1, then the force is 100?
No. Okay, so let's say the weight was 100, Alexandra. If the weight was 100 and the coefficient of friction was 1, then that would mean that 100 newtons of friction would be the result of that, of the two surfaces sliding. But if the coefficient of friction was only 0.5, then it would be 50. Now, if the weight was 200 and the coefficient of friction was 1, we would end up with 200 newtons of friction.
Is it always going to be like weight is 100, so friction is 100?
No, not exactly. Let me show you the equation, and then we have a problem. If it still doesn't make sense after that, then make sure you ask me. All right. So here, let me show you what the equation is. So the equation is the force of friction equals mu, which is the coefficient of friction, times the normal force. How I write this out and how I'll write it out for us for the rest of the time is that the force of friction is equal to mu, this is the Greek letter mu, times the normal force, or the perpendicular force. So this would be the friction force. This would be how much friction there is. This would be the normal force, or how hard the two surfaces are being squeezed together. And then this right here is the coefficient of friction. And like I said, that funky symbol, the reason that I actually copied this is from your book. This funky symbol, lots of people have trouble like understanding what that is. They think it's a W or something when I write it. Sorry about that. It is the Greek letter mu. That's what it is. So the force of friction equals coefficient of friction times the normal force. FF equals mu times the perpendicular force. And something that I didn't mention, you guys, because anytime you see something that's a coefficient, there are no units. It's unitless. This is telling you what percent of this force gets translated into friction. Is it 50%, 40%, 60%, 20%, 100%, right? That's all that it's saying. So let's see how we would apply this equation. Right? Here's our problem. So I want to know what is the coefficient of friction. That's my question mark. And I want to know what it is between a wood block and a tile floor. If a force of 200 newtons, so I have an applied force of 200 newtons. I'm applying it to a 5 kilogram wood block, and it produces an acceleration of 20 meters per second squared. So, it might be helpful if I draw a little picture of this. So here I have my wood block. It's on a floor, right? I'm going to have one force that's pushing on it with 200 newtons. I'm going to have friction as an opposing force. It's going to be trying to slow me down. Okay? Now, the mass of this block is 5 kilograms, and the acceleration of this block is going to be 20 meters per second squared. And it'll be in the same direction as the applied force. In this problem, This is going to be a multi-step problem. It's actually going to have 3 steps, all right? The very first thing we need to do is we need to figure out what that net force is. So the net force is equal to mass times acceleration. When we're done figuring out the net force, then we can figure out how much friction we have. So we'll take all the applied forces, the forces that are making it go faster, and subtract it from the opposing forces. That's just friction. Then once we know that, then we can plug in the force of friction. Oops. We can plug in the force of friction to our new equation, which is the force of friction equals the coefficient of friction times the normal force. So this is the first part we got to do. F net equals m times a, so that would be 5 times 20, and it will be 100 newtons. So that'll be our net force. Now that net force, that has to go into this equation right here. So I have the net force of 100. My applied force was 200. And then I have my opposing force, which will end up being friction. Friction is the only thing trying to slow me down. Let me write this so I don't look like a total crazy person. There we go. Now, to solve for this, you guys, the 200 is being added. So because it's being added, I want to subtract it from both sides. When I subtract 200 from both sides, I'll get negative 100 equals negative opposing force. Now I don't want to know the negative opposing force, so I would divide both sides by negative 1, and I would just get that the opposing force is 100 newtons. Now, it just happened to be 100. It's not always going to be 100. Just for this problem, it happened to be 100. I probably made it that way yesterday because I didn't want to have to pull out a calculator.
So I have a question.
Yeah.
So the forces should never be negative. You always want everything to be positive.
Well, it depends on how you want to think about it. Because friction is an opposing force, it actually is negative, right? But the way that we've written it here, we're going to take the applied forces minus the opposing forces. Because of the equation and the way we did this, it'll end up being positive. If you wrote that friction was negative 100, I would not count that wrong. Because friction is an opposing force, we usually think of it as a negative force. We usually think of it as acting in the negative direction. Does that make sense?
Yeah.
Okay. So now I'm going to take this opposing force is friction. Friction is the only force that's slowing this object down. So I would plug that in, and it would be 100 equals the coefficient of friction times the normal force. Now we didn't figure out that normal force, right? The normal force, you guys, is equal to the weight when it's on a flat surface. It's equal to mass times gravity. So the mass here was 5. Gravity is 9.8. You multiply those together, and it will be 49 newtons. So the normal force, or the force that's pushing these two surfaces together, is going to be 49 newtons. Now we want to solve for mu. Got to divide both sides by 49. So 100 divided by 49, it's going to be 2 point something.
.04.
2.04. And there are no units. It's just saying that if there's 49 newtons in normal force, you're going to get 2.04 times that as friction. So like I said, most of the time mu is between 0 and 1, but it can be bigger than 1. This would be a big coefficient of friction. Like think about, really good rubber deck shoes and a really good surface by the pool, like a non-skid surface. When I have those two surfaces together, friction would be very high. So I want to stop at this point. Does anybody have questions right now?
Yeah, I just feel like we're using so many n's. Is that like fine?
Yeah, okay, so the n's here, and this is why I changed up our equation. The n's here are units, so these are newtons. Every time I have a force, the unit is going to be newtons. So force, newtons. Force, that should be newtons. Right? Force is in newtons. That's why we're not going to use the equation from the book, because the equation from the book uses this capital N. I think it's a little too confusing, right?
Mm-hmm.
So when you see an N, that's going to be a unit. It just means newtons. It's just the unit for force.
Okay, and then what if it's like F and F, the friction one? Do we just put F?
Yeah. Well, force of friction. The units will always be newtons. I dropped my units there. I'm sorry.
Oh, okay.
I keep dropping my units. That's my fault.
No, that's fine. I was just a little confused.
Yeah. No. You're confused because of me.
Okay.
All right. So, can I make this problem a little tiny bit harder? I know you guys are ready for a little more of a challenge. All right. What if I have that box, and instead of that box being on a flat surface like the floor, what if it was on a ramp? If it's on a ramp, then the weight is not going to be the perpendicular force. So in this example, right, this force represents the weight, because the weight always points exactly straight down, right? Oops. The weight always points exactly straight down. But right here, the normal force is perpendicular into the surface. That's not perpendicular into the surface. So it's actually going to be just a portion of that weight, not the whole weight. If I were to take the components of the weight in the x and the y, like I want you to think about this for a second. What if I took my axis, my x and y axis, and I spun it? And I spun it so that it matched the surface. Okay, so it's matching the surface of the inclined plane. I want to know what's the vector that would complete this triangle, right? So there's an x, there's a y, and this would be the resultant, right? I want to break this. I want to break the weight down into its x and y components in this funky way of like spinning my axis. So the normal force for this, or the perpendicular force, it's not going to be the weight, it'll be a portion of the weight. So in this drawing right here, this force would be the normal force. This one right there. The weight is going to point straight down towards the center of the earth. And then this force right here, this is going to be something that we're going to call the parallel force. This component, it's not an actual force, it's a component of the weight, and this part of the weight, that's going to make it slide down the ramp. Now the steeper I make the ramp, the bigger the component of the weight is in the parallel direction, and the faster it'll slide down the ramp. the less steep I make the ramp, the bigger the weight component, or the component that's pushing straight into the surface, that's perpendicular to the surface, that'll get bigger. And so the less steep I make the ramp, the bigger friction gets, because the perpendicular force will get bigger. Now, how would we calculate this out? I'm going to show you. I'm not going to do anything but go to a slightly different slide, right? Same picture. But all I did is I changed this a little bit. So remember, our X and our Y axis, we're pretending that they're tilted, and they're running, the X axis is running parallel to the surface of whatever incline we're on. Now, if we do that, you guys, this might look familiar to you, this little table, right? We did these, we did those tables when we did vectors, right? So I'm going to split this into its X and Y component. Now, to do that, I told you, always take the angle that touches the X-axis. Because if you always take the angle that touches the X-axis, what that means is the X component will always be the hypotenuse times the cosine of the angle. The Y component will always be the hypotenuse times the sine. Because in our little drawing here, if I were to, I'm going to relocate. Come on, go away. If I were to relocate this vector, if I were to just move it over here, you guys can see these are supposed to be the same thing. The Y vector is the opposite side, and the X vector, that is the adjacent side. So the adjacent side, cosine, the opposite side would be sine. All right? So this will always be true. So another way of thinking about this, you guys, is that the normal force, if we have an incline, right, the normal force is always going to be equal to the weight times the sine of the angle, and the force that's running parallel to the surface, that's always going to be the weight times the cosine of the angle. If you guys want to, you could write those down with your equations. In fact, I probably would if I were you.
So the y-axis is the normal force then?
I'm sorry, say that again?
So the y-axis is the normal force then?
Yes, the y-axis here would be the normal force. Now, you guys, this angle is always going to match this angle on your incline. And this angle is always going to match this angle. They're similar triangles. So, can we do a problem? Let's do a problem with this. So let's say that I have a 20 kilogram block. Here's my 20 kilogram block. So the mass of this block, I'm going to write it in here, 20 kg. Okay. Now this block is sliding down my ramp at a constant speed. So that means the acceleration is 0 meters per second squared, right? Because it's sliding down at a constant speed. Now, if the acceleration is 0, what is the net force? Can someone tell me?
0.
It's going to be 0. Thank you. Okay, and then if we go over here, I'm just going to have you think this through for a second. I have force net equals all the applied forces minus all the opposing forces. If the net force is 0, right? I would have 0 equals the applied forces minus the opposing forces. The only way that can happen is if all the applied forces equal all the opposing forces, right? Well, there's only 2 forces that are acting on this block. I have a portion of the weight here, which we're going to call the perpendicular force. That portion of the weight is going to try to make it slide down the ramp. So this will end up being my applied force, right? That'll go here in applied forces. And then I'm going to have a force that's opposing motion. That'll be friction. So that would be an opposing force. So for this problem, you guys, the force that's trying to make it slide down the ramp and the force of friction, they have to be the same. They're equal and opposite. So they're going to cancel each other out. Okay. Oh, and I didn't give the incline. Let's say that this is a 30-degree incline, which would mean that's 30 degrees and this is 60 degrees. So if we use those angles, we'll make this 60 degrees. And I'll have the mass, which is 20, times 9.8, times the cosine of 60. Oh, I made that ugly. All right, times the cosine of 60. That's going to equal 20 times 9.8 times the sine of 60. Now, do you guys see that the 20 and 9.8, those are going to cancel? Oh, wait. I'm sorry. 20 times 9.8 times sine of 60 times mu. I got to get rid of my... because the force of friction, remember the force of friction is mu times the normal force. And here the normal force is 20 times 9.8 times the sine of 60 and then times mu. So if I do the math here, you guys, I'm running out of space. I'm going to copy this because this is looking like a mess. Clone page. Okay. So I'm going to move some of this stuff out of my way here. Also going to move all of this. All right. So I'll move my drawing. We'll make this clear. So remember, the parallel force is just the portion of the weight that's sliding down the ramp. Friction is going to be mu times the normal force, which is 20 times 9.8 times the sine of 60. Now, does everybody agree that the 20 times the 9.8, that those will cancel out? Does everybody see that? So that's not always going to be true, but it's true here because there's only 2 forces. And then what that leaves me with is the cosine of 60 equals mu times the sine of 60. To get mu by itself, divide both sides by the sine of 60. And for this problem, mu is going to be the cosine of 60 times the sine of 60. If I punch that in my calculator, you guys can probably do it faster than me. I get it to be 0.58. Can someone confirm that with me?
I got 0.6, but I think that's close enough.
Oh, 0.6. Okay, yeah. It's probably just rounding error somewhere. I may have rounded it in my calculator.
We're supposed to do cos 60 divided by sine 60.
That's right. And here's the other thing, and this actually affected a few people on the last test. Another reason why you show your work, you need to make sure that your calculators, you guys, are in degree mode, not radian mode. I mean, for this you'll get the same answer, but you know, in physics we're just going to use degrees.